Morning, everyone. So this is Joseph. He's got a rather interesting gear here, and it's going to work too. I know that. With that, it's Joseph.
Hi guys. So thank you for joining to this talk. I really hope that you guys will enjoy it. So what I'm going to talk about is this research and how I broke this WingOS. What I'm going to do is to discuss about some introduction about this WingOS thing is. Then we will discuss some scenarios and attack surface that we have with this OS and the devices. Then I will describe with full technical details some critical vulnerabilities, and then I will try to make a demo with these two devices, with an exploit that I did for trying to exploit one of the vulnerabilities. And then after that, we will discuss some conclusions. So what the hell is this WingOS? So basically, it's an embedded Linux operating system with its own proprietary stuff in the kernel, like they have their own proprietary drivers, they have their own proprietary socket address family and stuff like that. So originally it was created by Motorola, but now it's property of Extreme Networks. We'll discuss about it in a couple of minutes. Then the architecture is MIPS N32. At least the devices that I've been working with during this research were MIPS N32. And mainly is used for wireless access points and wireless controllers. And as far as I know, there is no public information or previous research on reported vulnerabilities about this OS, as far as I know, at least. So from Extreme Networks website, we can get some high-level details about this OS. Like, for instance, here is saying that it's for WLAN architectures and it's designed to scale efficiently from the smallest networks to large geographically dispersed deployments and stuff like that. So from the website, you can get more or less an idea and high-level details of this OS. So we have a web interface, a typical web interface where we can set a lot of stuff. I mean, the web interface is huge. And it also has vulnerabilities, but I didn't want to focus this research about web vulnerabilities, so we won't discuss web vulnerabilities during this talk. But also we have the typical command line interface, similar to the Cisco IOS, where you can, you have like different type of commands and combinations of commands where you can set the device. And this command line interface is restricted, meaning that from here you can't access to the operating system, the Linux operating system that it's running in the background. So devices using this WingOS. So I didn't get an official list of devices affected, but based on public information, for instance, from Extreme Networks website, we can see a list of Wing access points and controllers that uses this operating system. But as this is not official, this list could be even bigger in the case of Extreme Networks. But also we have Motorola devices and Zebra devices because, as I said, Motorola created this OS, so they have also their devices with this OS. And then Zebra bought this part of the business from Motorola, and that's why we also have Zebra devices with this OS. And then at the end, Extreme Networks bought this part of the business from Zebra. So basically, that's why we have Motorola access points, Motorola controllers, Zebra devices, and Extreme Networks devices running with this operating system. And also, we got the Contron device. So this particular one is important because all this research started because of this. Contron is a company that makes embedded devices for different industries, such as the aircraft industry and the train industry and stuff like that. So one of my coworkers in IOActive, Ruben Santa Marta, said, "Hey guys, here is an interesting target. This is an access point that is widely used in aircrafts by many airlines around the world. So this could be an interesting target for a research project." And then I thought, yeah, this might be fun. And yeah, it ended up being pretty fun. So basically, this is a box that it has some special connectors to comply with the aircraft regulations, the aircraft industry regulations. But basically inside, we got that Motorola AP7131 access point. So where we can find these devices? As we can see, for instance, in this picture from the internet, from an aircraft, they are actually installing that Motorola access point at the ceiling of the aircraft. So as I was saying, it's widely used in aircrafts by many airlines around the world. We got some other pictures from the internet where we can see the control box, where inside it's that particular Motorola access point. And yeah, it appears that they are installing these access points at the ceiling of the aircraft, but I don't know if maybe in other types of aircrafts they are installing the access point in other places. I have no idea. So from the Extreme Networks website and some case studies that we can find on the internet, we can see that these devices are also used in other different scenarios and industries, such as smart buildings, smart cities, healthcare, government, obviously small and big enterprises networks, I don't know, in a lot of different scenarios. Let's see some examples quickly. This is, for instance, a Motorola case study where we can see that the AP7161 and the 9500 controller are used in more than 200 subway stations in the New York City subway to provide Wi-Fi to the passengers. Then also we got container ports, global electronics manufacturers such as Isola in this case, and different facilities, universities such as this one. Also, even in mines, this case study from Zebra explains how these devices are used in the Westmoreland Coal Company in mines. I don't know, Saigon City in Vietnam, where they have more than 1,500 access points installed to provide Wi-Fi. Casinos, resorts, Nanjing University in China, another example. Hospitals, MWR facilities, case study, even apparently in military bases, as we can see in this case study. So as you can see, in a lot of different scenarios and industries. So for the attack surface and scenarios, I divided two, and this is mainly because the aircraft scenario is a little bit different and it has some particularities, and the other scenario, it's basically the rest of the scenarios that we got. So all of this stuff is focusing the remote pre-authenticated vulnerabilities that I found and the vulnerabilities that we will discuss later. So first we have the attack surface of the Ethernet cable, meaning like if the attacker has physical access to the access point, he can just connect the cable to the device, to any port or to an administrative port. And then he could, if he can reach the vulnerable UDP service and MIN services, then technically the attacker could exploit the issues. Of course, in the case of the aircraft, this is less likely, right? Because if the access point is at the ceiling, I don't know, I think that's unlikely. But I don't know, still it's a possibility. But also these vulnerabilities are technically possible to exploit over the air through the Wi-Fi connection. And also in the aircraft scenario, we got another attack surface, which is pivoting from the satellite modem to the access point from the ground. Let me explain this a little bit. So I don't know if you guys are familiar with my coworker's Ruben Santa Marta research. He recently spoke about this in Black Hat, in the last call for SATCOM security. So basically he was able, from the internet, just using a regular internet connection, nothing special, to hack and compromise satellite modems of aircrafts that are actually flying on the air. So then, based on that, we saw that, based on some information that we saw on the internet, that the attacker should be able to reach from the satellite modem the access point which is running the WingOS. So this could be another attack surface. And of course, I must say that the safety of the aircraft in these attacks and stuff for the WingOS and everything, the safety of the aircraft is not at risk. It's only the communications. So this is one of the architectures, and this is the satellite modem that Ruben compromised. And this is the access point running the WingOS, and these are connected through the SMU server, so we're pretty sure that it should be possible to reach the access point from the satellite modem and exploit the WingOS vulnerabilities. Then the other scenarios basically are the rest, like outdoor access points or indoor access points. So again, the other attack surface is, again, if the attacker has physical access to the access point, just connect the Ethernet cable, and that's it. And this is more likely in outdoor access points, but also possible in indoor access points if the attacker is inside of the office or the building or whatever. But again, through the Wi-Fi, it's also technically possible, as we will see in the demo, to exploit some of these issues. And also, if the attacker is somehow inside the internal network, and if the attacker has connectivity to some of these devices, then obviously he could try to exploit the issues. So let's start with the vulnerabilities. The first one is not a really critical one, but it was a really important one for the research because it's a hidden root shell kind of backdoor. So, and yeah, when you get a root shell, the process of the research, it makes easier this process, the research. So, but it's a kind of privileged escalation vulnerability. Because you need access to this command line interface to get that root shell. So from the attacker's perspective, yeah, if the attacker somehow has access to the command line interface, it's good. He can do a lot of stuff. But if the attacker gets a root shell, then we can say that the device is completely compromised. So here we can see in this picture in some forums, some guys asking about this service start shell command that gets you into the native operating system, but he says that Motorola may not disclose the required password to mere customers. So I was trying to find information about this start shell command. So all I got was like forums like that, people asking about it, but that's all I got. Even if we read the WingOS manual, we can see that yes, we have a start shell command, which provides shell access, but that's all you get. So when you execute this command, you get this like last password used password with this MAC address, and then this password prompt asking to the user to type the password. So one of you guys might think here like, okay, so it's telling me what is the last password used, so I'm gonna try password in lowercase letters, but obviously it's not gonna work here. So then since we got access to the firmware image, then we are going to start to statically reverse engineer some binaries to find out how this works. So based on the strings, we can see here the last password used string. And then here is going to call this validate map password function. And depending on the return value, it's going to reach this basic block where it's going to get the root shell. So let's get inside this validate map password function. Then again, it's going to call this other one, get last map password function, where it's going to open this file, etc2 IMIS password file. And the content of this file is this particular string. And this is the default value in every WingOS, this string inside that file. Then after that, with the content of that file, it's going to execute these instructions in this loop. So to play around with Unicorn, I emulated this code. I don't know if you guys know or are familiar with Unicorn, but it's an OSO framework that uses QEMU in the background and allows you to emulate several architectures. But of course, in order to emulate the code, you need some previous reverse engineering job or work. For instance, here you need to know what register points to your input, the buffer where we have the contents of that file, and also you need to know the register that points to the buffer where we will have the result of the operations. So I was using the Python API for Unicorn, and it's pretty simple. So you can emulate the instructions and provide the register values and create your buffer. And inside that buffer, we have the content of that file. And then after the execution of the emulation, we are printing out here the buffer where we have the result, which is these bytes, the result. So if we look at it carefully, we can see that this was the string that we had inside the file. So when the code is reading each ASCII character, then we got each hex byte for each ASCII character. And after that, this is the result that we got after those operations in that loop. So we can see that these bytes are these guys here. So basically, it's meaning that this is hex. Then after that, it's going to call a RC4 decryption routine. It's going to try to decrypt the content of that file, I mean the hex bytes after those operations in the loop, with this static key. Hi Sabina, how are you doing? Bye. No, nice key. And yeah, so in this case, after the decryption, the result is going to be the password string in lowercase letter, which makes sense because we were in the get last password, and that's why it was printing out here like last password used, password in lowercase letters. Then after that, the code is going to get the MAC address of the device. And then with the MAC address, it's going to execute these other instructions in this loop, and basically it's doing some operations with the MAC, like adding some numbers to each byte of the MAC. Like here, the first byte is adding 0, then the second byte is adding 1, and then 2, 3, 4, and so on. And then after that, what it's going to do is call another RC4 decryption routine. So it's going to decrypt password, so which is the result for the last RC4 decryption. But now it's with this key, the MAC address with those operations that we were talking about. And finally, after that, it's going to execute these other instructions, which I also emulated to play around with Unicorn. But basically, these instructions are making sure that the result is only lowercase letters. So here is the emulation, as you can see, and in my device, for my MAC address, this is the valid password, which is only lowercase letters. And then you can finally access to the root cell. Then in the code, we can see that after the password is granted, it's going to open again that file, the IMIS_password file. And then it's going to RC4 encrypt with the same key, the Hi Sabina, how are you doing key, the password that the user typed when the password was granted. Meaning that the next time you're going to execute the service start shell command, the password is going to be different. That's why I call this like a kind of a dynamic password, because the next time it's going to be the same, and you will have to do the whole thing to calculate the password. So here you have the overall process in case you later want to check with the slides. And yeah, and finally, in the code, also we can see that since we got access to the root cell, then creating this file, allow root, in etc, then you can make it persistent. And then all the time that you execute the command, it's not going to ask for any password again. Okay, so now, since now we have root cell, we can start to try to see more stuff about this OS. For instance, to check what services are running by default. And for instance, we can see that there are several ports like this 3799 UDP port, which is listening over all the IP addresses. So in this case, it's the RIM process, the radio interface module. So we are going to see a remote pre-authenticated stack overflow of this service. But this particular one only affects older versions of the firmware. But I wanted to share with you guys this one. Because it seems that they tried to fix it, but they made another mistake, as we will see shortly. But yeah, so now from here is the typical stuff from protocol reverse engineering. So basically, we trace the sockets, and we know where the code is parsing the user's buffer. So in this case, in this recbfrom, we know that the buffer length is 1000 hex, which is pretty big. And then just reading the code and following how the code is parsing the user's buffer, we can see that there is one particular memcpy where the source and the size are completely controlled by the user, and the destination is a stack buffer. So it's a typical stack buffer overflow. So we are here. Here's where we have in this red block the recv from, and here's where we have the call to this function, where inside we have that particular vulnerable memcpy. So what we need to do right now is the typical reverse engineering stuff, like to find out how to get from here to there, just reading the code, and build your own Python client to reach that particular memcpy. So this is one of the Python client to reach that Stack Overflow. So as I said, this only affects old versions of the firmware, but based on information that I got from the Contron website, the Contron devices that are used in aircrafts, apparently some of them could be vulnerable, as I saw in the website that they were running older versions of the firmware. So apparently they tried to fix this Stack Overflow. So here in newer versions of the firmware, so we can see here that they are checking the size of the memcpy, which is user control. But if it's bigger than this value, then it's not going to reach that vulnerable memcpy. Instead, it's going to execute this print function that is going to generate this crash dump, and then it's going to kill the process. So yeah, this is the Python code to reach that. And so yeah, you can kill the process, but the process, it will restart immediately. But the problem here is that there is a watchdog in this system that checks if this process is alive, because this process apparently is critical for the operating system. So if you execute this Python script like 2 or 3 times in a row, then the watchdog is going to check that the ring process is not alive, and then the whole operating system is going to be rebooted. That's why I call this like global denial of service. Then let's move on to the Mint vulnerabilities. I mean, there are other UDP services with issues, but we don't have time to talk about them. So let's move on to the Mint issues. So when I was reverse engineering some of the binaries, then I realized that they were receiving data from some particular sockets. So when tracing these sockets, I realized that they were using non-standard values, such, for instance, the 32x value for the domain value, and some references such as this one, like local Mint address. So I wanted to know what the hell was this Mint thing. So there's not much information on the internet about this Mint thing, at least about how it works internally. Of course, obviously, there are information about how to set the devices to work with Mint and stuff like that. But yeah, basically, it's a layer 2, layer 3 proprietary protocol, originally also created by Motorola. And they have like 2 levels, level 1 for VLAN and level 2 for IP. So Mint is used mainly to communicate devices between them. So for instance, here we have these access points communicating between them through level 1 Mint, or this access point to this controller through level 2 Mint, or these 2 controllers through level 2 Mint as well. So yeah, when you trace some of the processes as well, you can see some stuff like the socket address family, which is non-standard, AF Mint, the port, and then the Mint address, which is the 4 last bytes of the MAC address. So yeah, they created their own proprietary socket address family in their kernel, the AF Mint. In my case, at least, I was using datagram sockets. So the goal here is to be able to create a client, so we can communicate with other devices using Mint. So we have 3 options here. It's like the first one, reverse engineer their kernel and try to make your own client and make it work in your Linux box, which is technically possible. Then another option could be to try to emulate the whole operating system on the kernel and then make your own Mint client, which is also technically possible, but could be a pain in the ass. And then the quickest one, which is the one I took, because I didn't want to spend too much time working on that. So find a way to build a client using their kernel. So basically what I'm doing is using a device as the attacker, So, and running my own Mint client in the operating system. But again, this is not the only option. I mean, an attacker could use the option 1 or option 2 and use its own Mint client in its Linux box or whatever. So attack scenarios using Mint. So yeah, if in my case, as I'm using a device as the attacker, then if the attacker connects its device to the network physically with the cable or through the Wi-Fi, then if he's able to reach other access points or controllers that are using Mint, then he can exploit the vulnerability. And of course, other scenario could be that the attacker remotely compromise one device, and then since he has access to the root cell, then exploit the Mint issues to other devices that are connected with. And then, yes, basically attack the Mint services that are running in access points and controllers. Controllers are also interesting because they are like kind of Windows domain controller, meaning that controllers can have like hundreds of access points connected. So if the attacker compromises one controller, then he could compromise hundreds of access points, and not only with the vulnerabilities, but also controllers has the ability to change the configuration remotely of the access points, and also even update the firmware of the access points remotely. So the way I created the Mint client in the OS, we have here in the OS modified Python interpreter. And they have also their own libraries, such as this one for sockets. And this allows us through Python to create AF-Mint sockets. So they have some Python compiled files in the operating system, and then reverse engineering those compiled files. I saw how to create my own Python client to communicate through Mint. So basically, here's the Mint address, which is in decimal, but is the 4 last bytes of the MAC address of the target, then the port, the buffer, and then you can create the AF-Mint socket, and then send data through Mint to the target. So one important thing about Mint is that we can expect to have Mint where in scenarios where we have several access points and controllers, because as I said, Mint is used to communications between devices. But also I wanted to check if standalone access points can also use Mint. So yes, technically, as I saw during my test and during the research, it's possible. As we can see here, the Mint in a standalone access point is enabled by default, because you can set standalone access points as virtual controllers, for instance. So the attacker what only needs to exploit these issues is to know the IP address of the target. I mean, there is no any kind of authentication. So this is the target, the attacker's device, this Motorola Black access point. So we only need to set controller host and the IP address, and then the Mint link is established. But this is not the only way to establish a Mint link. As far as I know, there are other ways. For instance, also if you connect an access point in the network, then the other access points could detect in an automatic way this new access point and establish the Mint link in an automatic way. And probably there are more ways, because I'm not an expert with this Mint thing. So yeah, so after that, in the attacker's device, we can see that with the show Mint neighbors, we can see that the Mint link is already established. So now we can communicate through Mint. So now we just need to find bugs in Mint services. So there are a lot of binaries and a lot of Mint services receiving data from sockets. So this example is from the HSD process. So this particular graph is one function, which is more or less big, receiving data from a Mint port, one specific Mint port. And we can see the typical pattern of this that looks like we got like switch case statements that probably are switching through an opcode or something for the protocol. So one of the first issues, pretty straightforward, it's again pre-auth heap overflow, where the user has control of the size and the source, and and the destination buffer is the heap. But the problem that we have here is that to reach that particular MCBY, we got to go to the case here in the switch case statement. This function is going to be executed, get session by MAC. And what it's going to do, this function, is to check if the MAC address that you have to send in your buffer, it's in a list of authenticated MAC addresses. If it's not there, then you won't reach that particular memcpy. So luckily, there is another case in the switch case statement where we can call this session alloc function, where we can add our fake MAC address in that particular list. So first, we just need to execute this Python code where we will add this fake MAC address, 4141414141, to that particular list. And then after that, since our fake MAC address is already there in that list, then we can reach that memcpy, the heap overflow memcpy, and here you can see in our buffer we are providing the fake MAC address, and the rest is the protocol stuff to reach the memcpy. And then here we have the crash of this memcpy, this heap overflow, which since we don't have modern exploit mitigations and the libc version is all in this operating system, it shouldn't be too complex to get code execution from this heap overflow. Then we got more heap overflows like this one, pretty much the same in another switch case statement, but basically it's exactly the same, that the source user control, size user control, and the destination is a heap buffer. Now, this is the vulnerability that I will try to use in the demo. So it's an Stack Overflow through Mint as well. So it's another memcpy where the destination buffer is a stack buffer, obviously. And the size is also user controlled, but the size and the source comes from the heap buffer, and it's the heap buffer that we were discussing before with the heap overflow. So the problem that we have here is that this is the memcpy that for the Stack Overflow. So if we want to reach the return address in the stack, our buffer has to be big enough to reach that. So the problem as the source comes from the heap, then we'll have to also overflow the heap buffer and also overflow the next chunk and the next chunk's metadata. And we could have problems with the libc sanity checks because if the sanity checks triggers here, then it could crash the process, and then it could ruin our exploit. But in this case, it's not going to be a problem because in between there are no allocations on freeze, and so it won't crash, and we will be able to reach the Stack Overflow after the heap overflow. So for the exploit, as I said, we don't have modern exploit mitigations. So we could think, okay, we just need to jump to our shellcode and that's it. But no. So if you guys are familiar with MIPS exploitation, there is a well-known problem. It's the cache incoherence problem. So we got in MIPS CPU with two different caches, the instruction cache and the data cache. And normally our payload, so our shellcode, it could be in the it could be stored in the data cache. So the problem is that when we try to jump to our shellcode in the memory, if the shellcode is still in the data cache and is not flashed, then we could end up trying to execute another instructions that are in the memory. So what we just need to do is to fill the data cache, and the one possibility is to fill the data cache to flash it, but it depends on how big it is this cache. Another option could be to call a blocking function such as sleep using ROP, and using ROP because we could think here like, okay, I'm going to write a small shellcode which calls sleep and that's it. But yeah, we could have the same problem, like that mini shellcode could be still at the cache, and then we won't be able to reach that. So that's why we're using ROP. And then after that, then the cache will be flashed and we can jump to our shellcode. So for the ROP exploit, from the epilogue of the function where we have the Stack Overflow, we can know what registers we have control with. So this is very useful for the route, obviously. And then this is the gadgets that I'm using to execute the sleep and then jump to the shellcode. And all of them are from the libc. For the shellcode, I'm using a standard reverse shellcode, not a big deal. But I mean, there are, on the internet we can find several MIPS shellcodes for Linux. Even Metasploit provides MIPS shellcodes. But, and this particular one is from Exploit database, but none of these are going to work in this system. And as far as I know, and I tried to find shellcodes that could work in this system, are not going to work. That's why mainly because this is MIPS N32. So MIPS N32 has some particularities. For instance, it uses 64-bit registers, but uses 32-bit memory addresses. But also what it has is different syscall codes. That's why the shellcodes are not going to work. So it's not a big deal. You can just open the libc and check the syscall codes for each APIs that your shellcode is calling. For instance, this is the socket function, and this is the syscall code for this function. And then after that, then you got your MIPS N32 shellcode that is going to work, which by the way is big endian. So for the exploit, yeah, so remember that I'm using the black access point as the attacker, and it's going to attack the white module access point that I have here. So this graph represents better the exploit, so you can understand better. And I'm going to exploit it through a mint exploit through the Wi-Fi. So this is the attacker's laptop, which is my Mac here. So I'm going to connect through the Wi-Fi to the target access point. That because the access point is providing a Wi-Fi, obviously. Then I have an Ethernet cable connected to the attacker's device, and using the internet sharing of macOS feature, then now the attacker's device can has connectivity to the target through the Wi-Fi. And then 3 basic steps. I'm going to run the netcat listener in my laptop. Then I'm going to execute the mint exploit, which will chain 3 different things, as I will explain. And then through the Wi-Fi, it's going to exploit the mint vulnerability, and then the reverse shell, it will connect back to my listener. So let's see if it works. Fingers crossed. So I'm connected to this access point, Moto test, which is the target device. And here is the AP713191FD80, which is the attacker's device. So with this command, oh, nice. Wait a second, please. So mint neighbors. Now we can see with this command that the mint link is already established between the attacker's device and the target. Then I'm going to access to the root cell. So we have this shell script which is going to execute 3 different Python scripts. The first one is the one that adds our fake MAC address in that particular list, so we can reach the heap overflow. Then the second one is going to trigger the heap overflow, so we are going to overflow the heap with our shellcode and rob gadgets. And then finally, we're going to execute or trigger the stack overflow, which that particular MCPY is going to get from the heap buffer, the shellcode and the rob gadgets. And also, I have here the netcat listener. So let's see if it works or not. There you go. So here we have the reverse shell and with as root, as you can see. And you can see here that this is the AP7131 36F3E0 device, which is the the target because the attacker was the 91 FD80. So yeah, so this is the exploit for one particular Mint vulnerability over the air through the Wi-Fi. So finally, as a conclusion, so Extreme Networks were really responsive to us, and they provided fixes and patches for most of the issues. Here I'm sharing with you guys the link where you can check the patches and some other information. But at the beginning, apparently they didn't understand well the impact of the issues, because also they were saying that none of the vulnerabilities can be directly exploited over the air, which is not true, as you just saw. And some other stuff, like for the Mint vulnerabilities, they were saying that the attacker must have access to a Wing device that has already been compromised. That's not true. I mean, I'm using my own device, so the attacker can use his own device, but also the attacker technically could create his own Mint client in his Linux box. So this is not a must. But yeah, we recently spoke with them, and then they realized that it was wrong, and they changed all this information, and they are accepting now that the vulnerabilities can be exploited over the air, and the attacker doesn't need to compromise a device to exploit the Mint issues and some other stuff. So that's good. So yeah. Finally, I think there is a lot of room for improvement in this operating system, because there are more vulnerabilities in this OS. So yeah, I know. Hopefully, with these lessons learned, they will fix in a proactive way more issues, and then we will have more secure WingOS devices out there. So that's it. So thank you very much. And if you have any questions, I'll be around here.